All right, so just we're studying anti-differentiation here. So the anti-differentiation, the process of finding y from dy dx. So this means if we're given a derivative function, or we know the derivative but we don't know the original function, can we think of an original function that would provide this derivative, or f of x from f dash of x? And so this is the reverse process of differentiation. It is called anti-differentiation. So this is from our text. So this sort of, what we've done already in differential calculus is we've had functions, so y or f of x, and we differentiate them, we get dy dx or f dash of x. Now, what we're looking at starting to think about now is, can we go the other way and, given one of these values, come back to this original function? So we've got an example here. We've got dy dx equals x squared. And from what we know of calculus, we should know that y equals x cubed. This would provide me, if I took the derivative of this, dy dx equals 3x squared. So obviously this function doesn't work. We need it to be multiplied by a constant here. So if I instead go, well, y equals, I'm using this 3 out the front. The 3 is the only bit that's wrong from this. So if I do this 3 out the front, if I multiply the original function by a third, then the 3 and the third would cancel out. So if we go 1/3 x cubed, and then we take the derivative, dy dx would equal 1/3, and then 3x squared, they would cancel out, and it would equal x squared. Now, this is the simplest form of this function, and I'm just going to bring this up because this is going to be important in integral calculus later. So this bit here is important, and we're going to call this is the, I'm going to label this now. I'm going to pick a different color because I'm going to show you another example. So this is the antiderivative of x squared. And it's the simplest function, which when differentiated gives us x squared. But we should notice here that if I have y equals 1/3 x cubed, and then I add a constant, I'm just going to use 2 for this. If I take the derivative of this, it equals 1/3 3x squared plus 0. It also equals, these will cancel, it'll also equal x squared. Now the important bit here is we call this one here the antiderivative of x squared because x squared was the derivative. So the antiderivative of x squared gave us our original function, which was x cubed. Now this one here doesn't count because it's more complicated. If we do every constant that's possible, we would end up with infinite solutions. So we're looking at the simplest one there. And this will become, as we do integral calculus, that will become even more important. So if f of x is a function where the derivative equals f of x, the derivative of f of x is f of x, the antiderivative of f of x is f of x. So we're sort of using a different notation because we've previously used that function notation. So here we're saying the derivative equals f of x. So let's just use a red, we'll use this end one here. So this is sort of saying that this original function, we're going to call this f of x. And if we take the derivative of this, it's f of x. So that's sort of the way we've done it. So we've taken the derivative and we've got that function. So that's how we link to those original ones there. The reason we're using this new capital F of x is because we're sort of talking about if we're given a function, we want to think about the step before it. So we needed a new notation. And so that's why we're using the capital F of x now. Now let's look at these problems here. So we've got find the antiderivative of x cubed. I've picked these straight from the text. These are the example ones. So just picked them so we've got an example one to do. So we're looking at if we're taking the derivative of dx of x cubed, this would equal 3x squared. So we're not, sorry, I've made a mistake in here. This is the exact problem we've just done. Let me erase the 3's because this should have been a 4. Okay, there we go, 4, so that would be 4x cubed. Oh, hang on a sec, I stuffed up again. I'm all over the shop. Okay, sorry, mental blank. Okay, so because we're finding the antiderivative of x cubed, we're looking for something that when you take the derivative, the result is x cubed. So the derivative of x to the 4, we know we always drop a degree, like every time we take the derivative, the power drops by 1. So we know that x to the 4 is going to give me an x cubed. So this is good, but it's not quite right because we're out by 4. We're 4 times too big, so we're going to now look at, well, therefore, if we go d dx, a quarter x to the 4, it's going to equal 4, not 4, sorry. It's going to equal 1/4, and then 4x to the 3. So that there is going to equal x cubed. So we can then sort of write here, therefore, the antiderivative of x cubed is 1/4 x to the 4. Okay, so this is the antiderivative here, this value we're getting here, and the derivative, so the derivative of the antiderivative is what we're looking at there. Find the antiderivative of x cubed. We're looking at what number, when we give it take the derivative, is going to give us that. So this next one here, we're looking at e to the 2x. So we're looking at, we need a value that would give us e to the 2x when we take the derivative of it. So if we just do the derivative of that, so we should know exponentials, they don't change the power. So if I go the derivative of e to the 2x, it's going to equal e to the 2x and then times the derivative of the power, which is 2. So we're out, we haven't got the value we want. We wanted to get e to the 2x. We've got this 2 here, which is going to be a little bit annoying. So what we're going to do here is we're going to then go, well, therefore, if I times this thing by a half, my original function was times by a half, that should fix the problem, e to the 2x, and that's going to equal 1/2 e to the 2x, and that will be times 2, which is going to equal e to the 2x, because let's just change to that, and that would cancel there. Okay. Oh, I need to write this sentence, so let's just be a bit lazy to save ourselves the time. Let's copy that. We'll paste that below here. So therefore, the antiderivative of e to the 2x is half e to the 2x. Okay, so our next one here, we're looking at finding the antiderivative of 1 over root x, which is x to the negative 1/2. So we're thinking about what derivative we could do that would do this. Now, you've got to remember that when you, I'm trying to think of the way to explain this the right way. So when we do the derivative, let's just think of y equals x, let's just go x squared. The derivative dy dx drops, so that becomes 2x here to the 1. So you notice how this power drops by 1. So this one here, we're looking at, well, the derivative, it's obviously this value here, let's just highlight it, has to be 1 bigger. So I'm looking at that and I think, well, that's going to be the derivative d dx of x to the half. And if I take that derivative, I get 1/2 x to the negative 1/2. So I'm almost there. It's not quite right. I've got this fraction out the front that I don't want. So I'm now going to consider, well, the derivative of 2x to the half would equal 2/2 x to the negative 1/2, which is good because the 2's cancel here, and that would equal 1 over x to the half, which equals 1 over square root x, which is our original function we got out. So can I paste that thing again, that sentence again? I can. How good. So just get rid of the variables from that one. And we've got here, therefore the antiderivative of 1 over root x is, it's going to be 2x to the half, or if we wanted to, we could have written this as 2 square root x. All right, thanks guys, that's good there. So jump into those questions there. This is important. This is a foundational skill of integral calculus, so please do get through all the questions in